My name is Emma Yee. I'm from Austin, Texas, and I'm a junior at Columbia University in the city of New York, where I study chemical engineering. This summer, I've been working at NASA Glenn Research Center in the Combustion branch. With the help of my mentor, Thomas Way, I've been performing preliminary testing of NASA's open-source version of the National Combustion Code. This code has the potential to significantly decrease the time it takes to design combustion systems. To use this code, I took a three-dimensional virtual model of a combustor system, which can be easily changed as a combustor design changes. I used the model to generate a three-dimensional array of points. I then used the code to calculate internal physiochemical processes occurring throughout the combustion system, such as velocity fields and enthalpy. With this code, one can see how each change in the combustor design will affect what is going on inside the combustor. This code is still in its intermediate stage. My job this summer is to find ways to improve the code's ability to output accurate temperature fields for combustion at atmospheric conditions. I started off by generating a three-dimensional tetrahedral mesh. I wanted to see if meshes made of tetrahedral elements would output better temperature field results when the code was run on them. Once I had a satisfactory mesh, I used the combustion code to run cold flow tests on the mesh. Cold flow is a scenario where only air is flowing through the model, nothing is burning. This establishes airflow patterns inside the model. I plotted the steady-state airflow results to visualize velocities, temperatures, pressures, etc. inside the model. Once I established accurate airflows, I began running virtual ignition tests with the code. I would specify where I wanted to inject fuel, the angle of the fuel spray, etc. I also specified the location and burn duration of a heating element to initialize the ignition process. My goal was to initialize fuel vaporization and ignition and create a self-sustaining flame. I ran dozens of virtual ignition tests, repeatedly refining my original mesh and changing many fuel input parameters. With my latest results, it appears that I have established a stable flame. Particles are burning at the same rate as they are being inputted. The temperature field shows the hottest region where the fuel is being injected. Carbon dioxide and water combustion products are being generated in the flame region. However, I will have to run this scenario for much longer and wait until the hot region at the end of the combustor exits the outlet. Then I will examine my final code output and compare it to experimental results from an actual combustor operating at the same conditions. By tweaking various parameters in my fuel ignition tests, I am trying to obtain temperature fields that closely resemble what actually happens in real life. Accurate temperature field generating capabilities will put the code one step closer to becoming a useful, reliable tool in the combustor design process. In this process, I got to experience firsthand how much time you save in the design process by using virtual models and computational engines, and I also got more familiar with the combustion process. And this internship has not only prepared me for my future classes as a chemical engineer, but it's also shown me some real-life applications of fluid dynamics and combustion equations.